Discover unbeatable deals and convenience at your neighborhood family fare supermarkets. Score exclusive deals, earn rewards, join clubs, and clip digital coupons for extra savings all in one place. Our exclusive offers bring savings straight to your card. Explore a wide range of local products that support your community. With easy pickup and delivery options, saving time and grocery shopping has never been easier. Family Fare is all about making your grocery experience easy and affordable at your one-stop shop for all your grocery needs. Family Fare in your neighborhood.
Woodhouse Chrysler Dodge Jeep Ram is bringing you more power, capability, and savings with the full lineup of new Ram trucks during the Black Friday sales event going on all month long. Lease a 2024 Ram 1500 Crew Cab Bighorn for $429 per month. Visit our 2 convenient Metro locations in Blair or Bellevue or online anytime. Lease for 42 months, 10,000 miles per year with approved credit. Tax, title, license extra. $2,500 down plus first payment and $299 doc fee due at signing. Example stock number BC230242. Offer expires 11/30/2023. See dealer for details.
This is SpaceTime, Series 24, Episode 100, for broadcast on the 6th of September 2021. Coming up on SpaceTime, the possible detection of a new type of gravitational wave, a break discovered in one of the Milky Way's majestic spiral arms, and the fastest asteroid ever seen. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists using a groundbreaking new high-frequency gravitational wave detector have made 2 possible detections which are sparking a lot of excitement. Researchers are yet to determine exactly what it is they've detected. The 2 events, which have never been seen before, were spotted during the device's first 153 days of operations. The study's authors say the detections could be signs of high-frequency gravitational waves generated by primordial black holes, or possibly even a cloud of dark matter particles. Gravitational waves were first predicted by Albert Einstein, who theorized that the movement of astronomical objects could cause waves in space-time curvature, sending ripples through the universe, almost like the waves caused by stones dropped in a flat pond. Like so much of his work, Einstein's prediction was proven correct in 2015 when a gravitational wave signal was detected for the first time by LIGO, the Laser Interferometer Gravitational Wave Observatory. Now, these were what's known as low-frequency gravitational waves, which are caused by things like merging neutron stars and black holes. LIGO comprises 2 identical facilities located at Livingston, Louisiana and Hanford, Washington State. Each LIGO observatory fires lasers into a beam splitter, which then shoots the beams along 2 perpendicular 4-kilometre-long tubes equipped with mirrored test masses at each end. The reflected laser light is then sent back to the detector, where eventually they should theoretically recombine. However, as a gravitational wave, generated by something like a moving mass or merging black holes, passes through the cosmos, it causes the very fabric of space-time to stretch and compress ever so slightly, by just a fraction of the diameter of a proton. Local space-time, including the 2 beam lines and the test masses, are stretched and compressed ever so slightly, leaving them out of phase, the signature of a gravitational wave event. Using multiple gravitational wave detectors allows scientists to determine the direction of the wave source. A 3rd detector called Virgo, which is located near Pisa in northern Italy, has further improved detection, while a 4th observatory, Japan's Kamioka Gravitational Wave Detector, is the first to be built underground. However, there are a number of hypotheses which suggest that primordial black holes, and possibly even dark matter, might also generate gravitational waves, but at higher frequencies, and this would require a different type of gravitational wave detection. The new detector, developed by the Australian Research Council's Centre of Excellence for Dark Matter Particle Physics and the University of Western Australia, uses an experimental quartz crystal bulk acoustic wave resonator. The detector centers around a quartz crystal disk, which vibrates at high frequencies due to acoustic waves traveling through the device. And these waves induce electric charge across the quartz disk, which are detected through conducting plates on the disk's outer surfaces. The resonator is connected to a superconducting quantum interference device, which acts as an extremely sensitive amplifier for the low-voltage signal from the bulk acoustic wave resonator. The assembly was then placed in multiple radiation shields to protect it from stray electromagnetic fields and cooled to a low temperature to allow low-energy acoustic vibrations from the quartz crystal to be detected as large voltages using the amplifier. The two newly discovered signals, whatever they are, have now been reported in the American Physical Society's journal APS Physics. One of the study's authors, Professor Michael Tobar from the University of Western Australia and the ARC Centre for Excellence in Dark Matter Particle Physics, says the team are now working to determine the actual nature of the signal, potentially confirming the detection of high-frequency gravitational waves. Of course, gravitational waves are just one possible candidate. Other possibilities include the presence of charged particles or mechanical stress buildup, a meteor event, or even an internal atomic process. Still, Tobar says it's exciting because this event has shown that the new detector is sensitive and giving results. But of course now scientists need to determine exactly what it is those results mean. This equipment is one of only two currently active in the world searching for high-frequency gravitational waves. And Tobar and colleagues have plans to extend the research, looking for even higher frequencies, where no other experiments have looked before. He says the next generation of experiment will involve cloning the existing detector and also a muon detector sensitive to cosmic particles. And if the two detectors find the presence of gravitational waves, that would be exciting.
So what happens, this is more akin to what's known as a resonant detector, resonant bar detector, where LIGO is a free mass detector. So what happens is that it's more like a mass spring system, and if that mass spring system is oscillating just due to ambient noise, like thermodynamics around it, just the kT of energy, if there's an extra energy comes in and kicks it, the resonator will start oscillating at a bigger amplitude and respond to that kick.
And your job's to work out what's causing the kick.
Yeah, because we built this system very isolated from anything. It's got shielding from the environment, and generally we just see the motion due to the random temperature, and we just monitor that random temperature. Then out of the 153 days, we saw two clear kicks that the crystal got. In the crystal, there's different modes of vibration, just like in a structure like a bridge or something, we'll have different modes of vibration at different frequencies.
Sure.
And when we're monitoring different frequencies, we noticed that these kicks only occur close to 5 megahertz. So we were monitoring one mode at 5 megahertz and another one, I think it was 8 or 9 megahertz, I can't remember exactly. And that one never saw this kick. It means that the energy of the gravity waves is determined by its frequency. If they were gravity waves, or the energy of the process we're detecting is around equivalent to 5 megahertz in frequency.
Right.
Energy is usually given by maybe Planck's constant times frequency. Whatever the energy of whatever the frequency of the gravity wave is, we detected around 5 megahertz, but we didn't see it in the other modes that were not at 5 megahertz. So there's some process happening that's giving the crystal a kick, a sort of like an impulse kick around the 5 megahertz in frequency.
And you can rule out things like quantum fluctuations, the Casimir effect?
Well, the Casimir effect's more of that's more like a random fluctuation like temperature, so that wouldn't give such a kick. So this has to be some sort of process signal that's coming in externally and kicking. So either it could be like relaxation in the crystal, but it's around, I don't know why that would be around 5 megahertz, or it could be an external excitation like gravity wave or a cosmic ray or something like that, giving it a kick. With the funding we had, we just built one system and then we just get it running. We kept it running and then we just looked at data. And it was a surprise to see these two events. And so now we have to determine what these events are. Back in 2014, Maxime, who was first author on the paper, and I worked out that these things would be sensitive to high-frequency gravity waves, and we published a proposal. Then we got some funding from the ARC to test some fundamental physics with our technology, and part of that grant was to look for these high-frequency gravity waves. So with the money we had, we built a system. We cooled to very low temperatures and read out with what's known as a superconducting quantum interference device, or a SQUID, which is a quantum-limited amplifier. And then we can measure the thermal noise. We were able to measure the temperature of the surroundings by looking at how the modes were excited. And we were able to calibrate the detector if a gravity wave did hit it. And then we teamed up with my ex-PhD student and now professor in Glasgow, Seong Heng, to see how we could, because he works on LIGO, on the data analysis in LIGO, but he came from our lab, and so we used to work together on this bigger resonant bar, niobium bar, that was here in the lab. This was at UWA back in the 80s and 90s, and it was a big 1.5 ton resonant bar, and myself, Eugene, who's also a co-author on the paper, were one of the main researchers. I did my PhD on that, and we looked at this big 1.5 ton niobium bar to detect gravity waves at about 700 hertz. And then I was realizing as then Maxime came to work with us from France, did his PhD in France, and because I was interested in his high Q quartz technology, and he brought that technology here to Perth, and we started using to a range of tests of fundamental physics, including a lot of different tests, not just gravity waves, quantum gravity and Lorentz invariance. We've used these devices. It occurred to me that these devices would also be sensitive to gravity waves, because I saw some papers who were trapping spheres with optics and looking at the resonant frequency of those trapped spheres to look for gravity waves. And it occurred to me that these were higher Q and had good properties, and we could look at 5 megahertz. Then Maxime and I went and calculated the sensitivity and published a proposal paper in 2014. That was before LIGO detected anything. And then we set about building it, and with our funding and resources, we finally built it and got a student who was Will Campbell working on it. And we got it running, and we got the data, and he looked at the data and found these events. And then we confirmed them with Seong Heng, who had a look at our data and confirmed that there was some smaller events with lower signal to noise ratio, but we couldn't with any confidence say they were events. But there was definitely 2 events we could say with confidence are events, and due to some external source of excitation. Now, we built the detector to detect gravity waves, so that's one possibility because we know it's sensitive. But to do proper, to determine whether they are, we have to build more than one and do cross correlations and make sure that they occur at the same time. We got these events occurring at the same time in 2 different modes, near 5 gigahertz. So whatever the process is, we know that they're occurring around 5 megahertz, and they have a certain, like an impulse, because it has a certain width and it can excite more than one mode. So we know that. And so now we want to build more than one system and do a proper job to work out what these are. And that is a step up in experimental physics, because we have to build all sorts of BETO systems. We've got to look for cosmic particles to make sure it's not cosmic particles exciting the system, and determine whether these are just maybe local stress releases in the crystal, or maybe some event coming from the cosmos, which could be gravity waves, or it could be cosmic rays, or because they can excite the crystal too. If it was cosmic rays, we might expect to see more events, unless they're really high energy events. We would have expected to see more.
Yeah, was there a reasonable comment?
Yeah, that's right. Could also be a dark matter WIMP particle, which is what our centre is. We've got a centre of excellence.
That would be very exciting.
Yeah. Well, whatever it is, we need to find out what they are. Right? Whatever we find out will be exciting, even if it's something more boring in the structure itself. It's still a finding that people haven't. We're going to find out something new. We need to find out what these events are.
Yeah, you've created a mystery.
That's right.
This carries on from LIGO and Virgo, and there's a new one in Japan as well, and they're looking at much lower frequencies.
That's
they're
right.
detecting things like merging black holes and neutron stars and things like this.
They're looking at expected events, which is expected in current physics. Up at 5 megahertz, not many signals are expected because it's a bit theoretical, but there are some predicted signals that could occur, and also if certain physics exists, like maybe an axion dark matter exists and you get a collapsing, you've got all these axions around the black hole and they collapse, they can make a high frequency gravity wave too that just emits as a burst. So there is now a group that is looking for high frequency gravity waves. There's a consortium, a worldwide consortium, which we're part of. They're looking for anywhere between a megahertz up to gigahertz high frequency gravity waves, which if detected will be new, which will be totally new physics. It's just like when high frequency electromagnetic radiation was discovered, gamma rays, that wasn't expected, but it led to a whole new astronomy. So we know gravity waves exist, so we should look for high frequency too, because if we discover them, it's a major finding in physics and will lead to major people thinking about what they are. So this is why we're pursuing this work. We have the technology to do it, and we find it interesting to do.
And so now you've got to build another one and the testing equipment to be able to compare the two and See what you
That's
see.
right. Well, what we want to do is build three, and we want to read out more than one mode. We in principle, we can use FPGAs and read out 16 modes at a time in one crystal. And if we had three such detectors reading out all those modes, we would get all the information we need to try and determine what these events are.
That's Professor Michael Tobar from the Australian Research Council's Centre of Excellence in Dark Matter Particle Physics and the University of Western Australia. And this is SpaceTime. Still to come, a break discovered in one of the Milky Way's majestic spiral arms, and the fastest asteroid ever seen. All that and more still to come on SpaceTime.
Woodhouse Chrysler Dodge Jeep Ram is bringing you more power, capability, and savings with the full lineup of new Ram trucks during the Black Friday sales event going on all month long. Lease a 2024 Ram 1500 Crew Cab Bighorn for $429 per month. Visit our 2 convenient metro locations in Blair or Bellevue or online anytime. Lease for 42 months, 10,000 miles per year with approved credit. Tax, title, license extra. $2,500 down plus first payment and $299 doc fee due at signing. Example stock number BC230242. Offer expires 11/30/2023. See dealer for details.
Astronomers have discovered what appears to be a break in one of the Milky Way's majestic spiral arms. The newly discovered feature, reported in the Journal of Astronomy and Astrophysics, offers fresh insights into the large-scale structure of our galaxy, which is difficult to study from Earth's position deep inside it. It's a bit like trying to see the forest for the trees. The spiral arm break is actually a previously unrecognized contingent of young stars and star-forming gas clouds sticking out from one of the Milky Way spiral arms, sort of like a splinter poking out of a plank of wood. Stretching out some 3,000 light-years, this is the first major structure identified with an orientation so dramatically different from that of the galactic arms. Astronomers have a rough idea of the size and shape of the Milky Way and its arms, but much remains unknown. That's because we're located deep inside the galaxy, and much of it is hidden behind foreground stars, gas, dust clouds, and of course the galactic bulge. Therefore, astronomers can really only infer a lot about the galaxy's structure indirectly. To learn more, the authors focused on a nearby portion of one of the galaxy's spectacular spirals, known as the Sagittarius Arm. Our solar system lies near a small partial arm called the Orion Spur, which is located between the Sagittarius and Perseus arms. The authors used infrared data from NASA's Spitzer Space Telescope to detect newborn stars nestled deep inside the molecular gas and dust clouds where they form. While the visible light from these new stars remains hidden by the surrounding clouds, Spitzer could see the infrared wavelengths which the stars are emitting. And because young stars and nebulae are thought to align closely with the shape of the arms they reside in, this provides astronomers with a two-dimensional map of where they are and consequently where the spiral arm is. To get a three-dimensional view of the arm segment, the authors turned to the European Space Agency's Gaia mission to measure the precise distances to these stars. The combined data revealed that the long, thin structure associated with the Sagittarius arm is made up of young stars moving at nearly the same velocity and in the same direction through space. The study's lead author, Michael Kuhn from Caltech, the California Institute of Technology, says a key property of spiral arms is how tightly they wind around a galaxy, which is measured by the arm's pitch angle. Now, a circle has a pitch angle of 0 degrees, and as the spiral becomes more and more open, the pitch angle increases. Most models of the Milky Way suggest the Sagittarius arm forms a spiral that has a pitch angle of around 12 degrees, but this newly discovered structure has a pitch angle of nearly 60. Similar structures, sometimes called spurs or feathers, are commonly found jutting out of the arms of other spiral galaxies, and for decades scientists have wondered if the Milky Way spiral arms is also dotted with these structures, or alternatively, whether it's all relatively smooth. The newly discovered features contain 4 well-known nebulae of breathtaking beauty. The Eagle Nebula, which contains the famous Pillars of Creation, the Omega Nebula, the Trifid Nebula, and the Lagoon Nebula. In the 1950s, astronomers made rough distance measurements to some of the stars in these nebulae, and from that were able to infer the existence of the Sagittarius arm. And it was that work which provided some of the first evidence of our Milky Way galaxy's spiral structure. This is SpaceTime. Still to come, the fastest asteroid ever seen, and a new study shows that Martian snow is awfully dusty. All that and more still to come on SpaceTime. Astronomers have discovered the fastest asteroid ever seen. The kilometre-wide space rock, named 2021 PH27, takes just 113 days to complete each orbit of the Sun. It is a highly elongated elliptical orbit, which takes it to well within 20 million kilometres of the Sun, and a semi-major axis of 70 million kilometres, meaning it crosses the orbits of both Mercury and Venus. Only the planet Mercury is known to have a shorter orbit and semi-major axis. It takes just 88 days to orbit the Sun. But the asteroid swings in much closer. So close, in fact, that the Sun's massive gravitational field causes it to experience the largest general relativistic effects of any known solar system object. Being so close also means its surface temperature is awfully high, exceeding 500 degrees Celsius. Astronomers discovered the asteroid using the 570 megapixel dark energy camera in Chile. 2021 PH27 is believed to be one of around 20 known Atira asteroids, whose orbits are completely interior of Earth's orbit around the Sun. Scientists think it probably began its life in the main asteroid belt between Mars and Jupiter, but then got dislodged by gravitational perturbations and disturbances and thrown in towards the inner planets, eventually drawing closer and closer to the Sun. However, its high orbital inclination of 32 degrees compared to the ecliptic suggests it might instead be an extinct comet from the outer solar system. Future observations of 2021 PH27 will shed more light on its origins. From the little we can tell so far, its orbit's probably very unstable over long periods of time, meaning it will likely eventually either collide with Mercury, Venus, or the Sun, or be ejected out from the inner solar system by the gravitational influence of the inner planets. Its discovery is somewhat of a triumph. See, astronomers have a hard time finding these interior asteroids because they're often hidden by the intense glare of the Sun. And their survival rate isn't all that great either. See, when they get so close to the Sun, they experience a variety of stresses, such as thermal stresses from the Sun's heat and physical stresses from gravitational tidal forces. These stresses could cause some of the more fragile asteroids to break apart. Understanding the population of asteroids interior of Earth's orbit around the Sun is important in order to complete the census of near-Earth asteroids, including some of the most likely Earth impactors that may approach the Earth during daylight and so would not easily be discovered. Because 2021 PH27 is so close to the Sun's massive gravitational field, it experiences some of the largest general relativistic effects of any known solar system object. This reveals itself as a slight angular deviation in the asteroid's elliptical orbit over time, a movement known as precession, which amounts to about 1 arc-minute per century. But we'll have to wait to find out more. See, the asteroid's now entering what's known as solar conjunction, when from our point of view here on Earth, it'll be seen to move behind the Sun, making observation impossible. Still, it's expected to return to visibility from Earth early in the new year, when new observations will be made to determine its orbit in more detail, at which time the asteroid will also be given an official name. This is SpaceTime. Still to come. A new study confirms that Martian snow is very dusty, and later in the science report, discovery of a concerning new variant of COVID-19. All that and more still to come on SpaceTime.
Woodhouse Chrysler Dodge Jeep Ram is bringing you more power, capability, and savings with the full lineup of new Ram trucks during the Black Friday sales event going on all month long. Lease a 2024 Ram 1500 Crew Cab Bighorn for $429 per month. Visit our 2 convenient Metro locations in Blair or Bellevue or online anytime. Lease for 42 months, 10,000 miles per year with approved credit. Tax, title, license extra. $2,500 down plus first payment and $299 doc fee to signing. Example stock number BC230242. Offer expires 11/30/2023. See dealer for details.
Hey, Cricket customers, Max with ads is included with your Cricket $60 unlimited plan at no additional cost. Nice! Max is the streaming platform where you can watch Scoob, Meg 2 The Trench, The Nightmare on Elm Street collection, and so much more. Remember me. Just log in with your Cricket username and password to experience Max on all your favorite devices.
We've never seen this before.
Max, the one to watch for a good scream with Cricket. Phone plan streams in standard definition. Programming subject to change. Fees, terms, and restrictions apply. See cricketwireless.com for details.
A new study has confirmed that Martian snow is actually very dusty. The findings, reported in the Journal of Geophysical Research, Planets, looked at the grain size of the dust in the red planet snow cover. These measurements are crucial in helping scientists determine how old the ice is and therefore how it was deposited. The findings are based on combining data from NASA's Phoenix Mars Lander mission and the agency's Mars Reconnaissance Orbiter, together with computer simulations used to predict snow and glacial ice brightness on Earth. The data allowed scientists to successfully match the brightness of the Martian ice and determine its dust content. One of the study's authors, Aditya Kula from Arizona State University, says because Mars is a dusty planet, much of its ice is also dusty and much darker than fresh snow seen on Earth. And the thing is, the dustier the ice is, the darker it is, and thus the warmer the ice gets, which can affect both its stability and its evolution through time. Under the right conditions, it also means that the ice could melt on Mars. Kula says there's a chance that this dusty and dark ice might melt a few centimetres down, and any subsurface liquid water produced from the melting would be protected from sublimating in Mars's ultra-thin atmosphere by the overlying blanket of ice. Based on their simulations, the authors predict that the ice dug up by the Mars Phoenix lander mission was formed from dusty snowfalls sometime over the last million years, which is similar to other ice deposits previously found across the Martian mid-latitudes. And this all supports the widely believed hypothesis that Mars has experienced multiple ice ages throughout its history. And it looks like the ice being exposed throughout the mid-latitudes of Mars is a remnant of this ancient dusty snowfall. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. Scientists have discovered a potentially new COVID-19 variant of interest, which they're classifying as C12. The mutation was first detected in South Africa back in May and has since spread to at least 7 other countries spanning Africa, Europe, Asia and New Zealand. A yet-to-be peer-reviewed study of the new variant, reported in the journal medRxiv, suggests that it's accumulated a high number of mutations, many already identified in the 4 primary variants of concern, alpha, beta, gamma and delta. But the authors warned there are also additional mutations which provide a fresh cause of concern. The World Health Organization says more than 8 million people have been killed by the COVID-19 coronavirus, with over 4.6 million confirmed fatalities and some 230 million people infected since the deadly disease was first spread out of Wuhan, China. A new study claims that people can change their sexual orientation once they're shown data indicating that sexuality exists on a spectrum. The findings, published in the journal Scientific Reports, are based on a sample of 460 individuals, including 232 females and 228 males, all of whom identified as being straight prior to the study. The subjects were each then given 2 short scientific papers to read. One of the papers claimed there are many graduations of sexual attraction towards men and women, and people can fall anywhere along the continuum, from exclusive attraction to males to exclusive attraction to females. The other paper claims sexual orientation can change over time, and thus be fluid. Compared to a control group, after reading the first article, participants were 28% more likely to identify as non-exclusively heterosexual and 19% more likely to indicate they were willing to engage in same-sex sexual activities. Similar, though slightly weaker effects were found when people read that sexual orientation is better characterized as fluid rather than stable throughout life. Paleontologists have identified 2 new species of dinosaur discovered in the Appalachian Mountains. The dinosaurs, reported in the Journal Royal Society Open Science, both date back some 85 million years to the late Cretaceous. One of the specimens is a large meat-eating theropod related to Tyrannosaur. It consists of a partial skeleton of a large predatory theropod, with some identification markers suggesting it's probably a Tyrannosaur. The specimen contains several features in its hind limbs similar to Droptosaurus, and it has massive claws on its forearms very unlike Tyrannosaurus rex. The other discovery is that of the partial skeleton of a plant-eating hadrosaur, which is providing important information on the evolution of the dinosaur's shoulder girdle. A new study has found that on average, people are swearing less now than what they were back in the 1990s. The findings, reported in the journal Text and Talk, looked at how swearing's changed in casual British English conversation between 1994 and 2014. Researchers compared the use of 16 of the UK's most common swear words, finding that people are swearing 27.6% less now than what they were back in the 1990s. In fact, swearing was down from 1,822 words per million spoken in 1994 to just 1,320 words per million in 2014. Researchers also found that the F word has finally overtaken bloody as the most popular expletive in the UK. Both have dropped in overall usage, but the F word was only down slightly, whereas bloody has seen an 80% fall in popularity. And that's left the door open for the S word to move up into second place, doubling in usage. Researchers also found that men are still far more likely to swear than women, and one's use of expletives tends to peak in your 20s. And while the use of obscene language is commonly seen as a sign that the speaker lacks vocabulary or even intelligence, numerous studies have shown that swearing relieves stress and has been linked with traits of verbal fluency, openness, and honesty. The Dunning-Kruger effect is a well-known hypothetical conjunctive bias, stating that people with a low understanding of a subject or task tend to overestimate their own ability to know that subject or perform that task. Conversely, people with a lot of knowledge about an issue tend to underestimate their own ability to understand the issue. The effect is named after psychologists David Dunning and Justin Kruger, and it best demonstrates the ability of some people to objectively evaluate their own level of competence. Tim Mendham from Australian Skeptics says it explains why people who believe in things like UFO and COVID-19 conspiracy theories are so confident about their facts.
Basically, it's a topic which crops up quite a lot as to why people believe things. And there's individual motivations of things they've seen or things they've experienced convince them that a certain paranormal event or a UFO or whatever is happening. There's also the idea of what's called the Dunning-Kruger effect, which is basically that people who don't have a lot of knowledge exaggerate to themselves, convince themselves that they have a lot more knowledge, so they understand things more. The reverse is also true, that people who do actually have a lot of knowledge or skills are more modest, even concerned that they don't have enough skills. So you get this sort of discontinuity between what you can do and what you can't do. And the suggestion is that people who don't have a lot of training in critical thinking or whatever, and you can call that education if you want to go down that path, have more confidence in what they believe than people who do have more training. Perhaps people with more training are exposed to more alternative explanations of things, or just uncertainty, if you like, about our knowledge. And in science would say nothing's 100% known in science, so the uncertainty is part of science, and that's a good thing because it encourages us to keep trying. But in some places where you have lower education, you have a greater confidence in your belief, and that includes paranormal and UFOs, because it's not only people of low intelligence, to explain more perhaps education, there are people with very high intelligence, but as soon as they get outside their area, they might then fall for the three-card trick and believe all sorts of strange things. And
that's the Nobel laureate syndrome, yes.
Nobel laureate we've published in our magazine about people who are well-known scientists receive the Nobel Prize for their work in a particular area, but take one step to one side, or they're past their use-by date, or they've retired or whatever, and they don't show the same critical thinking about everything, and they will endorse the strangest things going. But because they're Nobel Prize winners, there's a certain imprimatur to what they're saying. So people say, oh, he must be true, he's a Nobel Prize winner. Well, the thing about the skeptics is you find that intelligence is not equal critical thinking necessarily.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.